Wonderful good morning, good afternoon, and good evening, whatever time may be at your place. A very warm welcome to our new edition of CSM Explained. My name is Timo Eich. I am Business Development Manager at CSM, and I'm promised to you to do my very best to give you a good time and, what's more important, some exciting insights in today's topic: thermal testing and characterization of high voltage batteries. So as you all know, the HV battery is the heart of an electric vehicle, and this heart has to endure a lot in its lifetime. There are negative effects which shorten its lifetime, for example, mechanical stress, permanently charging and discharging, and of course, extremely high or low temperatures. And we all know what happens to people's heart if it is stressed too much. They could possibly have a heart attack. And in case of our battery, it could look like this. Well, it happens really seldomly, but if it happens, it draws a lot of attention. Let's say it in that words, okay? No one needs such pictures, and I think we can all agree on this one, right? So to avoid such incidents, we need a smart HV battery thermal management, because a good thermal management prevents that the temperatures inside the battery get out of control. A good thermal management is crucial for two things. It's crucial for safety. Safety for the battery, safety for the vehicle, safety for the passengers, safety for all traffic participants, and safety for all the people who live in the surroundings of a charging station, for example. That's number one. And number two is performance. Performance is also very important because people want a performant vehicle. They want to be sure that they come from A to B. And actually, a lot of people want to have fun on the way from A to B. Especially in Germany, we are really crazy with that. So performance is very, very important. And as you can see in this graphic down here, performance highly depends on temperatures our vehicle, and in particular our battery, is exposed to. So lithium-ion batteries have a comfort zone around 25 degrees centigrade, and if temperatures leave this comfort zone, things are happening inside of our battery, which influence both performance and safety. So if we go down this temperature scale, we see that internal resistances go up when it gets colder, and this leads to reduced power output. And if we go down to minus 25 degrees or below, the electrolytes of our battery might freeze if we do not have some kind of heating system. On the other side, if we go up, if we climb up the temperature scale, we also might get higher cell internal resistances, and those lead to the disintegration of the electrolytes. And if we go beyond 80 degrees centigrade and up to 100, 120 degrees, there might occur a thermal runaway, the worst state our battery can get into, because then the vehicle will simply burn. That is why we need a good thermal management. Well, in serious production vehicles, this thermal management draws its knowledge of temperatures from a few more or less well-placed sensors inside the battery. However, the number of sensors is way too small to draw conclusions in the development phase of HV batteries. We need a lot more sensors inside the battery during the development. And now you may have just asked yourself, why don't we just simulate this? And yes, that is the first step how it is done. What we see here is a pouch cell and an overlay of simulated temperature readings as a color chart. And now I show you what it looks like if you take real temperature readings using sensors and measuring devices. And you can see here that there's a huge difference between of what has been simulated and what has been measured with sensors. And that means two things. Number one, verification of simulation models with measured data is vital. And number two, only measurements on test benches and in road tests allow realistic testing. That's really important. And there are a lot of testing scenarios where real testing is needed. We need it for thermal characterization of HV batteries, including hotspot investigations and testing for thermal failure. We need it for the verification of our cooling systems, and we need it for the verification of temperature propagation models. Now, if we want to measure temperature inside of HV batteries, there are a lot of challenges for our measurement equipment. Because first of all, the equipment and especially the sensors have to be applicable at different cell types. If we have round cells, cylindrical cells, we have pouch cells, and we have prismatic cells. And if we measure at cell level, the sensors have to be positioned as exact as possible between the individual battery cells, because we have to transfer the positions of the simulated measurement points into reality as accurate as possible, because only exact positioning allows the verification of simulation models. And what's more, the positioning of sensors has to be 100% reproducible on several identical cells to allow a comparative analysis of temperature profiles. Of course, we also need temperature measurement on module level, and one big challenge is the routing of cables for several hundred measurement sensors, temperature sensors at very limited space, because of course the HV batteries are packed with a maximum of battery cells in a very confined space, and therefore we have very little space for sensors, additional cables, and measurement components inside the battery. And finally, we have to measure on battery level, for example, at bus bars, at charging electronics, and on the BMS. And if we sum up all of those needed sensors of all three levels, we get a huge number of sensors. We have accompanied projects with up to 500 temperature measuring points at different positions inside one single HV battery. That's really huge. And I want to share a true story, a story I have experienced myself when I was part of the sales team of CSM. Around 2013, an OEM of southern Germany called me and wanted an offer for 330 temperature channels. That are 42 thermal modules providing 8 channels each. And I was like, oh wow, what a project. And 2 weeks later, the order came in. I was really happy. And then 6 weeks later, they quoted the same amount of modules and ordered them instantly. And another 4 weeks later, they ordered another 35 modules. And I could hardly believe my luck. I was constantly thinking, how huge must their fleet of vehicles be if they need so many modules? And then I visited them. And when I was there, I asked them, how many vehicles did you instrument with all of those modules? And I think you can guess the answer. 3. Just 3 vehicles. They measured with over 300 sensors inside one single battery. And now I will show you how they did that and do until today, and why they are now going to switch over to a much better solution, which is the core of this speech. They measured with thermocouples in a high voltage safe design. And as you might know, those thermocouples lack accuracy due to the principle of the sensor technology. Class 1 thermocouples provide an accuracy of 1.5 Kelvin or 0.4% of the measured value. And this is oftentimes insufficient if we want to verify simulation models with the reality. Well, they might have used another type of thermal sensor, the PT100 or RTD sensor. We also offer high voltage safe modules for those, and the sensor variants of these, they are quite accurate. The sensors reach an accuracy of 0.3 Kelvin, but there are also some disadvantages for those RTDs. Because first of all, it is very, very difficult to position them precisely. And this was one of our key requirements if we want to perform comparative analysis of cells. Another big issue is that RTDs have to be used with a 4-wire technology if we want to have the good accuracy for those sensors. Because look, if we have to install that many sensors, and that's only one single battery module, the cabling effort explodes. And here is another issue. If we have that many sensors, it is difficult to correctly identify those sensors when all those cables are led outside the battery. It is only human that there will be miswiring of channels when setting up the system. Now we have to route all of those sensor cables through the battery, and here's the next problem, because we will get a huge cable density in that limited space. And what's more, analog sensor cables are prone to interference, especially if they are very long, and they have to be long if we want to route them all outside the battery to our measurement modules. And then one of the major problems arise if we want to lead the cables outside of the battery. We need lots of breakthroughs in the battery housing. It looks like cheese, like the picture you see down there. Look at the cheese. It's a real catastrophe because HV batteries should be operating completely sealed to prevent toxic gases from the electrolytes leaving the housing. And of course, we do not want humidity from the outside get into the battery. And finally, we have to connect all of those sensor cables to a lot of modules which have to be placed somewhere. And especially in road tests, that means that our trunk is full of measurement modules which take up a lot of space and also bring a certain weight with them. So to sum it up, we have a lot of requirements. We have even more challenges if we want to instrument batteries with classic measurement solutions utilizing this old topology. And this is why we need a totally new approach. And this new approach is a digital temperature measurement system, which is able to acquire up to 512 sensors with one single system. And we call it the high voltage detemp measurement system. The HV detemp provides a total system accuracy of 0.1 to 0.25 Kelvin, and that's really, really accurate. And that's why we have already ticked off the first item on our list of requirements. This system consists of 3 major parts, and we have our small, tiny, high voltage safe IC sensors. We have very small controller boards, controller modules, which collect the data from the sensors inside the battery. And we can connect several controllers from inside the battery and then lead one single cable out to the only part of the system which is placed outside the battery housing, the central unit here. Okay, let's take a closer look on those IC sensors. They are soldered onto an ultra-thin flexible circuit and measure temperatures on their bottom surface with pinpoint accuracy, and the measuring range extends from -40 up to 125 degrees centigrade. And if we take the encapsulation away for a better view, you can see how tiny this sensor is. It is only 0.5 millimeters high, which allows to fit the sensors between the cells without damaging those and without damaging the sensor. And of course, the flexible circuit is a little bit larger because it has to provide the soldering pads for the sensor cable. So the huge advantage of those IC sensors is that the signals are instantly digitized and therefore not susceptible to interference. And what's more, a digital sensor allows clear identification and assignment, and it minimizes errors by mixing up sensor cables. And finally, our IC sensor elements provide contact safety up to 1000 volts. And now we connect those IC sensors to our controller modules with special sensor cables. And for efficient wiring, we can group those sensors and create so-called sensor assemblies. But first of all, let's take a short look at the sensor cables. We have two versions of sensor cables. The orange ones, they are quite robust and in most cases the matter of choice. However, sometimes we need thinner cables, and those we see here on the right, they are not that robust but also provide up to 1000 volts contact protection. So using those cables, we can now create several sensor assemblies for different applications. We have a single sensor which is directly connected to a controller. This is the least efficient variant, but sometimes it is required if a single sensor has to be acquired completely isolated from other sensors, maybe because it is applied in a significantly different voltage potential. However, here one sensor blocks an entire port of a controller, and that is why additional assemblies are available. For example, 4 sensors daisy chained, which are connected to one port of the controller, or we create kind of star circuit with a small distribution board here, and we call that the star design. So with this and those different types of sensor assemblies, we can very easily create now an efficient network of sensors at various locations inside the HV battery, for example, between the cells, on bus bars, and on the BMS, and so on. And on the right, you can see, for instance, how it would look like in a very famous vehicle, which is named after a certain genius who invented AC voltage. Well, we still have the problem that we have to position those sensors very accurately. And to simplify that, we can use an ultra thin flexible circuit and arrange our sensors with pinpoint precision on it. Here we see an example with 4 sensors shaped as a stripe, and the sensors are connected via conductive tracks, and at the end of the stripe the sensor cable leads to the controller. And now we can arrange up to 20 IC sensors like this, and this could then look like follows. Here we see a prismatic cell which is instrumented with a more complex flexible circuit with 12 sensors. And we can now cookie cutter this for several battery cells. So we now have the solution for measuring temperature at identical cells on the exact same locations with reproducibly pinpoint accuracy of sensor arrangement. Now, if we take a look on our list of requirements, we can see that utilizing those IC sensors solves a lot of those issues. We can take temperature readings on different levels inside the battery with very high accuracy. We are not susceptible to electromagnetic interference any longer, and the application of the sensors is quite easy with all the sensor assemblies and flexible circuits. Okay, then let's talk about the controller. The controller, it provides the power supply for the IC sensors. It manages the assignment of the individual sensors, and it collects and transmits the digitized temperature readings on a bus system. One controller provides up to 16 ports, so we can connect 16 sensor assemblies with 4 sensors each to it. That makes a total of 64 temperature measurement points at one controller. And we can now daisy chain up to 8 of those controllers, which may be placed at different locations inside the battery. And that makes a total of up to 512 sensors. We have a bunch of controller types for different applications depending on which galvanic isolation is needed. Better isolated controllers have a reduced number of ports due to electrical limitations. So for nearly every use case, there's a controller available. And of course, we work on more depending on what customers need. So now we have placed all the sensors and all the controllers inside the HV battery, and we have also connected them with our isolated cables. And now we only have one single cable that we'll need to lead out of the battery. We only need one breakthrough, and that's definitely practicable. So we only generate a very, very low impact on our battery housing. And on our list of requirements, we can check off further points. We only claim very little space inside the battery because we have very tiny sensors and controllers. And in addition, we only lead one single cable out of the battery, which has a very, very low impact on the tightness and on the battery housing itself. And finally, this one cable leads to our central unit. The central unit controls the entire system. It manages the precise identification of both controllers and sensors, and it provides two galvanically isolated inputs, for example, for two different HV environments, or if we have sensors inside and outside the HV battery. And we only need one single measurement module outside of our battery. We only require very minimal space in our trunk. For comparison, this is what it would look like if we would do this the old way. This is like a battery looks if we use classic temperature measurement equipment. And people still do that until today. But we are now going to change that. Of course, this central unit is set up by a configuration software, and it transmits all of those up to 512 channels by a CAN bus interface, which is very easily connectable to any kind of data acquisition tools. And if we take one last look on our list of requirements, we can check off the final issues, the explicit identification of measuring points, as well as the minimal requirement of space outside of the battery. So the HV temp measurement system is what we call the next generation of high voltage safe temperature measurement technology for batteries, which is suitable for all existing and probably most of the upcoming battery architectures. I hope I could show you how thermal testing and characterizations of high voltage batteries can be done utilizing a completely new design of a digital temperature measurement system for various applications and use cases.